So the last problem last night, number 41, might have been a little bit too difficult, and you might have looked at her and been like, nope. So let's practice one state plan do conclude before we go on to today's material. Before we do that, just a quick refresher that if I were to take like a population of people and I took a random sample of size n and I've found a certain proportion of those who got more than 8 hours of sleep a night from my sample, I would take that p hat and I would graph all of the p hats on a dot plot. Here would be all my values for the p hat, right? And so the mean, this highest peak of p hat, is going to be my mu of my p hat, right? So this thing here is going to be mu of the p hat, and the mu of the p hat should approximate the true proportion of people who were able to sleep more than 8 hours. Let me fix that. Okay. Or 8 hours or more or something like that. But our standard deviation is p times 1 minus p over n, and then take the square root of the whole thing. So the square root of p times 1 minus p over n. So that was from yesterday. We had mean and standard deviation. So if we have a mean and we have a standard deviation, we can do a z-score. So that's what we're going to do. Here's the problem. A sample survey interviews an SRS of 267 college women. Suppose, as it's roughly true, that 70% of college women have been on a diet within the past 12 months. What's the probability that 75% or more of the women in the sample have been on a diet? Follow the 4-step process, as in state plan do conclude. So since you're watching this on your own pace, feel free to go backwards and forwards so that you can see this problem as I keep working. So let's start with the state. Pause it as you go and see if you could try to say out loud, what would the state be? Okay, so what is our state? We were given two numbers, right? We were given 0.7, like 70%, and then we were given 75%. And it said specifically, like, we want to find what's the likelihood that they could be like more than 75%. So that's what we're going to use for our state. We want to find the probability that p hat could be greater than or equal to 0.75. And then what we do is we just define what p is. This is the easiest way to do state because then you can just say p throughout this thing and you don't have to re-explain until you get to the conclusion what p means. And sometimes people don't write it in full sentences. They say like where p equals da 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 da, and they write what it would be, like the true purport where p is, and that would be like p equals, like down here, the true proportion of women who have been on a diet within the past 12 months. So don't necessarily need complete sentences, but you do need this whole statement that says true proportion. And true proportion means like what the population actually is of women who've been on a diet within the past 12 months. So we're moving on to the plan. The first thing I do in the plan is I state my N and my P. Now I stated this in complete sentences, but honestly, because you've already stated P before, it is okay for you to just state N and P. So I said we have an SRS of N equals 267 drawn from a population in which the proportion P of 0.70 of college women have been on a diet. So we're going to use the P that's assumed here, that's given to us in the problem. And I could just say, instead of all the sentences, I could say SRS N equals 267, P equals 0.70. And that would work. Then I need to talk about what my mean and my standard deviation are. So I have to, well, mean is pretty straightforward, right? I know that the mean of the p hat should be 0.70. So that's what I'm going to use. My mu of my p hat should be 0.70 because that's what was stated as the parameter in the problem. and mu of my p hat is always going to estimate that parameter. Okay, so then I need standard deviation. Well, I got to use that big formula. N p times 1 minus p divided by n, and then I need to take the square root of the whole thing. So great. I've done my SRS, I've done my mean, I've done my standard deviation. Oh, but we are not done yet. Remember how we said we have to check conditions? This is the biggest part of the plan from here on out. I can only do a z-score if I know that this is normal. And I can only calculate my standard deviation if I know that things are independent and that the proportions aren't going to change. So we're going to check our conditions, and this always goes in the plan portion. So I'm going to check the 10% condition. How am I going to do this? Since I don't know the huge population of college women in the US, I'm just going to be like, 267 times 10 is 2,670. There's more than 2,670 college women, period. Done. So that's the 10% condition. Then I have to check the large counts condition. So that's n times p equals this, and n times 1 minus p. And they both have to be greater than 10. So I would say both are at least 10, so it's approximately normal. And always we're going to use this word approximately normal. So I check the 10% to make sure that I can calculate the standard deviation. I check my large count so that I know that it's approximately normal so that I can do a z-score. The plan is sometimes the biggest section in this, honestly. All right, so now let's go on to the do. All right, so I wrote this out like if I were doing it by hand, but I want what's the proportion where p hat is greater than or equal to 0.75. And so that's how I would do a z-score. I would look for this in your work. I want to see the z-score. I don't necessarily need to see all of this stuff. I mean, I do need to see the answer here. I do need to see this picture, right, with the shading. And then I do need to see that this is my mean and this is my standard deviation. And then I might be like normal CDF, right? Because that's what we're going to do on our calculator. My lower looks like 0.75. My upper is a really big number. Doesn't really matter. My mean is 0.7 and my standard deviation is 0.0280. And then this is what I get for my answer. So now we need to put that into context with our conclude. Okay, so for the conclusion, I would say about 3.6% of all SRSs of size 267 will give a sample proportion that is 0.75 or greater. That's pretty low, but there's our conclusion. And that's how we do a state plan do conclude. What we're going to be talking about today is looking at two sample proportions. So yesterday, everything we did was with one sample. Now we're stepping it up a notch and we're looking at two samples. Yay! Okay, so comparing two proportions. So I'm looking at two different proportions. So there's going to be like population 1, where I have like some estimated parameter of P1, and then the statistic is going to be P hat 1, and then the sample size is N1. And then I have a second population or treatment where the parameter is P2, the statistic is P2 hat, or P hat 2, and then my sample size is N2. So what we're going to look at is we're going to perform inference, and inference is just where we make a decision or a conclusion using the difference between the two statistics to predict the difference between the parameters. Now, we just did a whole chapter where we looked at differences, so we know how to do this. Just to refresh about variability, let's look at this next slide. Okay, so here is one example here of the sampling distribution of population 1. And here is the sampling distribution of population 2. So these are all this is my P hat 1 and this is P hat 2 sampling distribution. And if I look at this, this is p hat 1 minus p hat 2. And you'll notice that this variability of this one is so much greater than the other two. Because that's right. When we take a difference, we have to add the variance to get the variability of a difference. Okay. So now we've got to talk about what does the sampling distribution look like of p hat 1 minus p hat 2. So essentially we have to sort of state some background information here. So we're choosing a simple random sample of size n1 from population 1. And the proportion of successes we're going to call p1. And then there is an independent, separate, completely different, simple random sample of size n2 from population 2 with proportions of successes p2. If all of that is true, then the sampling distribution of p hat 1 minus p hat 2 is approximately normal as long as the large counts condition is met. But we have to meet it for both samples, which means we're going to have to go n1 times p1 is greater than or equal to 10, and n1 times 1 minus p1 is greater than or equal to 10, and then n2 times p2 is greater than 10, and n2 times 1 minus p2 is greater than 10. They all have to be greater than or equal to 10, all of them. So we've got to check 4 things for the large counts. Okay. That allows us to be able to do a z-score. Let's talk about the mean. So the mean of p hat 1 minus p hat 2 is just going to be mu p hat 1 minus p hat 2. That one's not so bad. But the standard deviation. Okay, y'all. When we take differences with random variables, we add the variance. Here it is. Okay, so the standard deviation is the variance of the first population plus the variance of the second, and then I got to take the square root. So is the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2, and the square root of the whole thing. And you're probably thinking, oh my God, I'm never going to remember this. That's right. You don't have to. It's in your blue book. It's there for you. In fact, when you start working on problems today, I'm going to have you grab a blue book so that you can do these problems, but it is there for you. Now, I can take the standard deviation as long as the 10% condition is met. So I have to make sure that both populations are both samples are less than 10% of the population. So I have to check that twice. Okay, that's a lot of work. So to reiterate, we need to always and forever check our conditions. So I'm going to check the large counts. I'm going to check the 10%. Okay, but that formula for standard deviation that we just looked at, that hellaciously long thing, is exactly correct only when we have two types of independence. Okay, independent samples. So we need to have completely independent samples that we can add the variance. If they're not independent, the proportions are all going to change. And we need to have independent observations within each sample. So when sampling without replacement, the actual value of the standard deviation is smaller than the formula suggests. However, if we need that 10%, the difference is negligible. And that's why we do the 10%, right? So those proportions don't change. Because let's face it, we always sample without replacement. So I'm going to be checking, did I have in two populations that are completely independent? Yep. Have I met 10% for each population? Like if have I met the 10% condition? Check. Then we are good. Okay, here's a visual representation of the sampling distribution. So I have p hat 1 minus p hat 2. There's my standard deviation. There's my mean. Is that simple? By simple, it's not simple, but there it is. There it is. Okay, let's look at a problem. Okay, so the first example that I was telling you about was really a study about homework. And what was found in school one was that 70% of the students were doing homework in school one, and 50% were doing their homework at school two. So let's suppose two students, Holland and Audrey, decide to replicate the homework study and compare students at H&A, which we'll call school one, and O'Day, which we'll call school two. Now, by the way, I'm just picking random schools. This is not any representation or true fact or true proportions for O'Day or Holy Names, just to be fair. Okay, so going back to the example, school one, so we said with a reported average of 70% for school one and 50% for school two. So we're taking the SRS of 100 students from H&A and 200 students from O'Day. Notice, not the same sample size. Guess what? I don't care. It doesn't have to be the same. It could be totally different sample sizes. It doesn't matter. These are independent, random, simple random samples. Okay. And then we're going to record the proportion of students who did their homework last night. When they're finished, they find the difference in their proportions. So what the students got when they did P-H&A minus P-O'Day is 0.10. And they're surprised to get a difference this small. So what I want you to do is we're going to describe the shape, center, and variability of the sampling distribution P-H&A minus P-O'Day. So notice the first thing I did was I defined what this was. I said P-H&A minus P-O'Day, right? I want to be very clear that you need to, whenever you're taking a difference between two random variables, we need to state which one is subtracted from the other. So I'm going to describe the shape, center, and variability. Then I'm going to find the probability of getting two proportions that are at less than or equal to 0.10, which is what they found, apart. And then I'm going to ask, should they be surprised by such a small difference? Okay, so let's look at shape, center, and variability, how we would describe the distribution. So the first thing I want to do is check my shape. Now, my dream world is that it's approximately normal, but the only way I can check that is if I check my large counts condition. So that's what I'll do. I'll go n times p of H&A times n times 1 minus p of H&A, and then n times p of O'Day, and n times 1 minus p of O'Day. And I will do all of these, and I get 70, 30, 100, and 100. Then I'm going to say, well, since all are at least 10, the sampling distribution of P-H&A minus P of O'Day is approximately normal. Great, I've done my shape. The next thing I'm going to do is my center, and that one's pretty straightforward. I just subtract. And I subtract of what I was expecting to find, the P's, not the P hat, right? So 0.7 minus 0.5 is 0.2. So that's what I would expect to see as my mean. And then the variability, right? Again, 0.7 times 0.3 over 100, 0.5 times 0.5 over 200, add them together, take the square root, and I get 0.0578. So now I have a mean right here of 0.2, and now I have a variability, right? Well, if I have a mean and I have a variability, I can find a z-score, and that's what we're going to do next. Okay, so let's go on to that z-score. So we wanted to find in the original problem, P-H&A minus P-O'Day was less than or equal to 10%. So we have P hat H&A minus P hat O'Day was 0.1. Now that was given to us that we wanted to check. So that's my statistic. So I'm going to use my stat here, and notice my stat is going to go right. I'm going to use my z-score. So stat minus parameter. And again, this is what I determined from our estimate of H&A was 70 and O'Day was 50, and we had a difference of 0.2. And then here's my standard deviation. So when I do that, I got a z-score of negative 1.72. Notice I drew my beautiful, and not that beautiful, distribution with my mean and the number that I was looking for, my stat, my 0.1, and I shaded it. I stated the mean and the standard deviation next to the n there. So I have all the things. I also wrote down what I would do with my calculator using normal CDF, lower a really big negative number and upper 0.1 with a mean of 0.2 and a standard deviation of 0.058. And you're probably saying, Amisho, do I really need a negative really big number when I know that it's proportions and the smallest number is possibly 0? I don't even think about that. I just always do a negative really large number. It will work out the same. So I just choose negative really big numbers so I don't have to think through it and just do the same thing every time. Okay, so when I do that, I get 0.042059. So there's only a 4% chance of getting a value in sample proportions as smaller than the value of 0.1 reported by Audrey and Holland. This seems unusual, which means that that is actually what they got. So that means that this proportion of HNA being 70 and O'Day being 50 must not be true. Like, these must be lies. Like, there's no way that can be true if this is what she found, because there's only a 4% chance of that happening, assuming that the PHNA minus P O'Day is equal to 0.20. So assuming this is true, there's no way that could have happened. So this must not be true. All right, that was quite a lot. Feel free to pause, rewind, do whatever you need to, and then you can work on your problems in the book. There is a quiz tomorrow, but you got this.